Section 3. Worlds Within Worlds, the Story of Nuclear Energy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Blaine Aidan McCoy, Riverside, California, 2019. Mass and Energy. In 1900, it began to dawn on physicists that there was a vast store of energy within the atom, a store no one earlier had imagined existed. The sheer size of the energy store in the atom, millions of times that known to exist in the form of chemical energy, seemed unbelievable at first. Yet that size quickly came to make sense as a result of a line of research that seemed, at the beginning, to have nothing to do with energy. Suppose a ball were thrown forward at a velocity of 20 kilometers per hour by a man on top of a flat car that is moving forward at 20 kilometers an hour. To someone watching from the roadside, the ball would appear to be traveling at 40 kilometers an hour. The velocity of the thrower is added to the velocity of the ball. If the ball were thrown forward at 20 kilometers an hour by a man on top of a flat car that is moving backward at 20 kilometers an hour, then the ball, to someone watching from the roadside, would seem to be not moving at all after it left the hand of the thrower. It would just drop to the ground. There seemed no reason in the 19th century to suppose that light didn't behave in the same fashion. It was known to travel at the enormous speed of just a trifle under 300,000 kilometers per second, while Earth moved in its orbit about the Sun at a speed of about 30 kilometers per second. Surely, if a beam of light beginning at some earthbound source shone in the direction of Earth's travel, it ought to move at a speed of 300,030 kilometers per second. If it shone in the opposite direction, against Earth's motion, it ought to move at a speed of 299,970 kilometers per second. Could such a small difference in an enormous speed be detected? The German-American physicist Albert Abraham Michelson, 1852 to 1931, had invented a delicate instrument, the interferometer, that could compare the velocities of different beams of light with great precision. In 1887, he and a co-worker, the American chemist Edward Williams Morley, 1838 to 1923, tried to measure the comparative speeds of light using beams headed in different directions. Some of this work was performed at the U.S. Naval Academy and some at the Case Institute. The results of the Michelson-Morley experiment were unexpected. It showed no difference in the measured speed of light, no matter what the direction of the beam, whether it went in the direction of the Earth's movement, or against it, or at any angle to it. The speed of light always appeared to be exactly the same. To explain this, the German-Swiss-American scientist Albert Einstein, 1879 to 1955, advanced his special theory of relativity in 1905. According to Einstein's view, speeds could not merely be added. A ball thrown forward at 20 kilometers an hour by a man moving at 20 kilometers an hour in the same direction would not seem to be going 40 kilometers an hour to an observer at the roadside. It would seem to be going very slightly less than 40 kilometers an hour, so slightly less that the difference couldn't be measured. However, as speeds grew higher and higher, the discrepancy in the addition grew greater and greater, according to a formula Einstein derived, until, at velocities of tens of thousands of kilometers per hour, that discrepancy could be easily measured. At the speed of light, which Einstein showed was a limiting velocity that an observer could never reach, the discrepancy became so great that the speed of the light source, however great, added or subtracted 0 to or from the speed of light. Accompanying this were all sorts of other effects. It could be shown by Einstein's reasoning that no object possessing mass could move faster than the speed of light. What's more, as an object moved faster and faster, its length in the direction of motion, as measured by a stationary observer, grew shorter and shorter, while its mass grew greater and greater. At 260,000 kilometers per second, its length in the direction of movement was only half what it was at rest, and its mass was twice what it was. As the speed of light was approached, its length would approach 0 in the direction of motion, while its mass would approach the infinite. Could this really be so? Ordinary objects never moved so fast as to make their lengths and masses show any measurable change. What about subatomic particles, however, which moved at tens of thousands of kilometers per second? The German physicist Alfred Heinrich Bucherer, 1863 to 1927, reported in 1908 that speeding electrons did gain in mass, just the amount predicted by Einstein's theory. The increased mass with energy has been confirmed with great precision in recent years. Einstein's special theory of relativity has met many experimental tests exactly ever since, and it is generally accepted by physicists today. Einstein's theory gave rise to something else as well. Einstein deduced that mass was a form of energy. He worked out a relationship, the mass-energy equivalence, that is expressed as follows: E equals mc squared, where E represents energy, m is mass, and c is the speed of light. If mass is measured in grams and the speed of light is measured in centimeters per second, then the equation will yield the energy in a unit called ergs. It turns out that 1 gram of mass is equal to 900 billion ergs of energy. The erg is a very small unit of energy, but 900 billion of them mount up. The energy equivalent of 1 gram of mass, and remember that a gram in ordinary units is only 1/28th of an ounce, would keep a 100-watt light bulb burning for 35,000 years. It is this vast difference between the tiny quantity of mass and the huge amount of energy to which it is equivalent that obscured the relationship over the years. When a chemical reaction liberates energy, the mass of the materials undergoing the reaction decreases slightly, but very slightly. Suppose, for instance, a gallon of gasoline is burned. The gallon of gasoline has a mass of 2,800 grams and combines with about 10,000 grams of oxygen to form carbon dioxide and water, yielding 1.35 billion ergs. That's a lot of energy, and it will drive an automobile for some 25 to 30 kilometers.